Hello everyone, and welcome to today's webinar on engineering data analysis. In today's presentation, we'll introduce the MATLAB environment and talk about how it can complement and integrate with work you may be doing in Excel. I always like to start off with a preview of something we'll be working towards today. We're going to start with some data inside of Excel. This is some aircraft sensor data recorded over time. You can see we have some timestamps here and a number of sensors recording over time. And I'd like you to think about the amount of time and effort it might take you to turn a spreadsheet of numbers like this into even a simple report like we have here. This report documents the problem we're working on, captures all of our analysis steps in a clear and reproducible manner, captures any outputs like graphs and charts throughout our entire workflow, and even includes some advanced analytics like building a machine learning model to predict future sensor values. In our demonstration today, we'll see how in MATLAB you can create reports like this while writing almost no code yourself. And towards the end, we'll talk about how you can co-develop in both MATLAB and Excel to try to get the best of both worlds, and also deploy what you've built in MATLAB to Excel users so that they can use it for free. But before we get into any of that, my name is Adam Fillion, and I'm a Principal Product Marketing Manager here at MathWorks, which means I spend most of my time building teaching and demonstration materials to help people learn MATLAB, like you're going to see today. A quick agenda. We're going to start by talking about what is engineering data analysis and what are some of the special challenges that come with it. Then we'll move into a MATLAB demo where we'll spend most of our time today modeling some flight sensor data. After we see a bit of what MATLAB has to offer, we'll move back to slides and we'll talk about how you can grow your skills in MATLAB and combine MATLAB with Excel. And we'll end today with some learning resources you can use after today's presentation. So when we talk about data analysis, we're really talking about a workflow. And that workflow always starts with data access. Today we'll focus on accessing Excel data from MATLAB, but this data could be coming from anywhere. It could be coming from databases or hardware, or we might be streaming it off the web or from the cloud. But wherever our data is coming from, we want to get through this step as quickly and easily as possible so we can get to what we like to call explore and discover. And this is ideally where you want to spend the majority of your time. This is where all the really interesting things happen, where we'll make different visualizations of our data, maybe clean up some anomalies, build models on top of it, develop algorithms, maybe even build a nice UI front end. But you can do all the analysis in the world, it's not really worth anything until you share it with other people. And so that's the last step. How can we take the work we've done and share it with others in different formats? You already saw one quick, very simple kind of report we might share, but you can also take the work that you've built and deploy it to others so that they can use it. Now, we've laid this out in kind of a linear workflow here, but if you've ever done this kind of work before, you know this is anything but linear. You'll need to import lots of different data from different sources and create different visualizations. Some you'll want to keep and reuse, and other ones you can throw away. And you'll want to share your results with many different people in different formats. So a key theme for today is going to be automation. How can we do things the easy way once and then have MATLAB automate that task so we can do it over and over? But this kind of general data analysis you can do in many different platforms. MATLAB really starts to differentiate itself when you are analyzing engineering data, because engineering data introduces special challenges. When I talk about engineering data, I'm typically referring to time series sensor data. So this is data that might be recorded in a laboratory using equipment like you see on screen here, or it might be sensor data that is being recorded or streamed live from equipment that has been deployed into the field, like a car or an aircraft. This data is often measuring many different things at different data types or levels of data precision at different sample rates. And because it's recorded over time, preserving the order of those data points is very important. And because it's recorded over time, we often need to analyze this data in a time-dependent or time-aware fashion. So consider, as a simple example, this noisy sinusoid here. The human eye can easily identify that spike in the middle that I've highlighted with a red circle as being anomalous and potentially an outlier we might want to remove. However, this is something we wouldn't find with just a traditional mean and standard deviation. We need something a bit more sophisticated. In addition, we might want to look at our data in the frequency domain, where we can see not just the sensor's value over time, like in the top plot, but also see the magnitude of the different frequencies that it contains. This can add a lot of additional insight to what's happening inside of our data. And all of this time-dependent and frequency domain analysis happens in the presence of complex groupings in our data. Engineering data often comes from fleets of equipment, and when I say fleet, people often think of cars or buses, but a fleet is really any collection of physical assets that are generating sensor data. So you might have a fleet of robots on a manufacturing line, or a fleet of wearable devices, or a fleet of wind turbines or EV charging stations. Inside of each fleet are the individual assets. There are many individual vehicles inside of a fleet. Each vehicle takes many trips, and each trip, its data is often provided as a separate file. These files are often broken up into different data packets or chunks, sometimes called messages. Each message contains the different sensor signals, and each signal might be recording in a different level of precision and sampling frequency. And then each signal has its time value pairs, which we often need to store explicitly because it might not be regularly sampled. And over time, we may need to ask questions at different levels of granularity within this hierarchy of data. We might start more simply by looking at a single vehicle and analyzing some of its data over time from different trips and different files. But later, we may need to compare the overall performance of different fleets against each other, but only for trips that start and stop within a certain geographic region. Now, MATLAB provides specialized tools to address all of these challenges. Because today is an introductory session and we don't have a lot of time, we're not going to get into the details of all of them today, but I want you to keep them in mind and think about how they might apply to your work as we go through the rest of this presentation. One of the things MATLAB does for you is it puts the focus on your analysis rather than your data. So on the left here, we have a very small amount of engineering data in Excel. And as is always the case in Excel, the focus is on our data. We're sitting here staring at the raw numeric values. If I want to do some analysis, like find the mean of this column, well, the inputs and outputs are going to be locations. We need to find an empty location in our spreadsheet to store this analysis. And the input, again, is going to be a location. And it's up to the reader who comes across this later to figure out what does B2 to B11 mean in this context. When we execute our analysis, we're again back to looking at the data, and that analysis is hidden. It's still there, but you need to know to go click on that cell to see what the analysis is. MATLAB takes these relationships and inverts them. In a few minutes, when we hop into our MATLAB demo, we'll talk about everything that's going on in the MATLAB desktop. The thing I want you to take away from this right now is that we're not sitting here staring at the data. The data's still there. It's in a place we call the workspace. The workspace is sort of like MATLAB's memory space. It's where it shows you all the different data it has in memory and knows about, and you can play around with. And different pieces of data in MATLAB are stored in what we call variables. Variables are just named containers for data in MATLAB. In this case, we took the data that was inside of Excel and we read it into a variable in MATLAB we called weather table. So in MATLAB, by default, the data is hidden, but you can still see it. We can open this variable up and look at the raw values. It looks a lot like it did inside of Excel. But in MATLAB, it's our analysis that takes center stage and persists. So if I wanted to take the average of a column in MATLAB, we write that pretty similarly to how we would write a formula in Excel, but now the inputs and outputs are going to be variables rather than locations. So as an input to the mean function, we're going to tell it look at the weather table variable, and then with the dot syntax, tell it look at the temp column. Likewise, the output is going to be another named variable that gets stored back in our workspace. So I've worked with a lot of Excel users over the years, and their first concern is typically if they're a strong enough programmer or coder to use MATLAB. But if you're comfortable doing in Excel what I did on this slide, just finding an empty place and saying equals some formula, you already know all the programming you need to be successful with MATLAB. The bigger challenge is this mental shift from focusing on your data to focusing on your analysis, and from the inputs and outputs of that analysis being locations to instead being variables. If you can master that shift, you'll pick up MATLAB very easily. And one of the things that MATLAB does to make that very easy to pick up is it simplifies programming with low-code tools. Low-code is a term from the software industry that describes tools that let you rapidly build software without needing to write a lot of code yourself. And we'll see a lot of examples of that today, but I wanted to show you a very quick one here. If you use MATLAB for any length of time, you'll quickly encounter the plot command. You can give it some X data and Y data, and it'll make a simple line chart. But you might not know how to customize it, like let's say add some axes labels or turn on grid lines as we're doing here. Well, you can see when you do different operations in MATLAB, often there's an interactive way to do it that will generate the code you need to programmatically do the same thing. And this has a lot of benefits to it. It creates a very shallow learning curve, so you can quickly start doing more complex things in MATLAB without needing to be a very strong programmer or know a lot of coding. But then at the same time, it'll teach you how to code because it's giving you the code you need to do the same thing. So these tools are great for beginners, but they're also not just for beginners. I've been writing MATLAB code almost every day for over 20 years now, and I still use these tools all the time because they help me get my job done faster, which is the thing I really care about. But with all that said, I think that's about enough for PowerPoint. Let's get started with our MATLAB demo. Our case study for today is we're going to be modeling some flight sensor data. This is public data provided to us by NASA, a number of sensors recorded throughout a flight from Halifax to Detroit. And our objective is a common one in the world of engineering. We're going to try to create a virtual sensor model. The idea here is we have some physical piece of equipment we're going to deploy out into the world. And after we deploy it, we want to continue to measure or monitor some part of that system. But after we deploy it, it becomes either very expensive or outright impossible to measure that part of the system directly. So instead, we're going to take some historical data we have, and we're going to try to build a mathematical model that can predict that value based on other lower cost or more readily available sensors. We're going to start with some data in an Excel file, and the approach we're going to take is we're going to read this into MATLAB, we're going to visualize it, explore it, clean up some sensor anomalies, then train a machine learning regression model to predict that state, and then document all of that in a simple report. And after that, we'll hop back to slides to finish out the presentation. But with that, let's go ahead and hop over to MATLAB. So here we are on the MATLAB desktop. We've got a number of windows we'll explain as each becomes relevant. And the first thing that I always think about is how am I going to document and reproduce the work that I do today? So to start, I'm going to come up to our Home tab, and I'm going to create a new live script. A live script is one of the ways you can capture and organize the work that you do in MATLAB. It's a little analogous to opening a new workbook in Excel. And this is a place not just for code, it's a richly formatted environment, almost like an executable document. So I can add things like, let's say, a title for my document, virtual sensor model. Looks like I'm having trouble spelling today. And we can add some comments for what are we going to do at the start of this script. Let's say I'm going to start by importing some Excel data. So I can add however many comments that I want here to explain what's going on. But we can add more than just text. We can add outside images and equations and hyperlinks and tables of content. Let's say this is good enough for the moment. And then we can interleave with these more human-readable comments and text MATLAB code in these shaded regions. Now to start, we want to import some Excel data, and we can see that over here in our current folder. The current folder window just shows us what directory MATLAB is currently looking at and working in, and this is the Excel file we saw earlier that we're going to work with today. Now, if you've used MATLAB at all before, I'm sure know how to import data from Excel. That's one of the first things people tend to learn when they're working in MATLAB. And there's many different ways to do it. I'm going to show you the easy way. I'm going to come up to this task menu up here in our tool strip. And this shows us a gallery of what we call live tasks. These tasks are small apps or little UIs that will embed directly into your live script and give you a point-and-click easy way to solve a certain problem, and then give you the code to programmatically do the same thing. And you can see there are tasks for importing data, creating plots, cleaning up data, especially the types of problems that tend to happen in engineering data, like smoothing out a noisy signal or getting outliers or removing trends. There's tasks for things like doing table joins and creating pivot tables in MATLAB. There's over 40 of these for different tasks in data analysis, engineering, and AI. We're going to start by getting the import data task. It's going to ask us to pick out a file. This supports any type of file that MATLAB recognizes, so not just Excel data, but also things like images and netcdf and HDF5. And this is automatically going to scan that file. It's going to take its best guess as to how it thinks we want to import it, and then it'll go ahead and run and import that data. You can see it'll give it a name, call it flight data, and it'll appear over here in our workspace. As we talked about back on the slides, the workspace is where we can see all the different data MATLAB knows about. And if we double click on any of these variables, we can open it up inside of the variable editor. Variable editor is a great place if you really want to dig into what those raw values are. Looks a lot like Excel, except here in MATLAB, this is not a place to do analysis. This is just a view of the data. The live task will also print out a preview of that data so we can see it embedded directly here. And just to give ourselves a bit more real estate, I'm going to maximize my live script. And instead of having the output over here on the right next to my analysis, I'm going to put it in line because it's more wide than it is tall and make it a bit more like a document. Okay, so the task took its best guess as to how it thinks we might want to import it. I can then customize those options, like what sheet do I want to read from, how do I want to read it in. Let's say I want just a basic table, very analogous to a table in Excel. And as we're doing this, behind the scenes, what it's really doing is it's generating and then running the code needed to do the same thing. And in this case, it's just a simple 2 lines. It's using the command called read table to read a table from Excel. Great place to read tabular data, not just from Excel, but other file types as well, like CSV and Parquet. It's giving that the name of our file, and actually not just the name, but the full path, just to be safe. And then is storing that result in a named variable, flight data. This will read that data into MATLAB. And then if you ever want to display or just print out the contents of a variable, just tell MATLAB to execute that variable name, and that'll print out the result. Now, once we're done fiddling around inside of the task, we can collapse it to kind of hide the UI and not have it take up so much space. But if we're really done with the interactive part and we're confident we're not going to need that again, we can also take this and just convert it back to just pure executable code. So this completely deletes the UI, and now we're back to code no different than if we had written it ourselves by hand at the keyboard. So this solves that first step of data access. We've gotten data from Excel into MATLAB. Now that we've gotten that first step solved, we probably want to save what we're doing, call it whatever we want. Let's call it my analysis. And now that we've saved it, you can see back in our current folder window, that's where our file popped up. It just saved it in the current folder. Okay, so now that we've gotten some data into MATLAB, what's the next thing we might want to do with it? I hear a lot of different answers at this point. I know some people who like to jump straight into statistical analysis, but personally, I always like to plot it. I find plotting data is the fastest, easiest way to figure out what's going on inside of it. So I'm going to create a new section inside of our live script. Sections in the script can be run independently, and I can add some more comments down here. Let's say I want to visualize our sensor data. And of course, I could write some code to visualize this, but again, I'm going to do it the easy way, and I'm going to grab the create plot live task. And this task will show us a gallery of the many, many different types of charts and plots that there are in MATLAB. Let's say I want to start with a basic line plot. And then I can pick from my workspace, what data do I want to visualize? Let's say I want to put the time measurements on the x-axis, and let's say I want to start with altitude, because I have a pretty good idea of what the altitude should look like throughout a flight. And that'll visualize that for me. So now I can see altitude versus time. It starts very low near the ground and looks like it plateaus around 31,000 feet. So that was the cruise altitude for this flight. And graphics in MATLAB are not just static images, they're interactive. We can zoom, we can pan, we can explore what's going on. And again, as we're interacting with things in MATLAB, it's giving us the option to automatically generate the equivalent code. So if I really like this particular zoom and I want to hard code it so that every single time I create this plot, I'm going to zoom in on this one part of it, MATLAB's giving me the code I need to do that. But in this case, maybe I don't really need it. We looked at the altitude. Maybe I want to look at the true airspeed. The true airspeed is the sensor we eventually want to be able to predict. And again, kind of a sensible profile. True airspeed grows very quickly during takeoff, levels out during cruise. Makes a lot of sense. Maybe I want to look at some of the other sensors, like oil pressure. Oh, and here we can see some anomalies in the data. So you can see that occasionally the oil pressure is dropping all the way down to 0 and then popping right back up. And clearly that can't be happening in reality. This is what we call a sensor dropout. It's a very common problem in engineering data, where a sensor will very briefly stop reporting real data and will just output some kind of default value like 0. So if we want to analyze this data and build a model on top of it, this is something we're going to need to clean up. And if it's happening in the oil pressure, we should probably check the oil temperature. And again, we can see something similar dropping down to almost negative 400 degrees. I don't care what temperature scale you're using, that obviously can't be correct. So it's really useful to quickly explore these different sensors over time, but this is a flight. I want to see the flight path. So let's look at latitude and longitude. And okay, that's technically doing what I asked it to do. This is a line plot of latitude and longitude, but I really want to see this on a map. So we can go back up, we can either search or just scroll through our gallery until we find something that looks right. Let's say we want to look at a geoplot. Okay, and that looks a lot better. So now we can see the flight path from Halifax to Detroit, like NASA said. But we can again see a different kind of anomaly here, where at the very end of the flight, the GPS coordinates briefly go to 0, 0. So this is kind of similar to what happened with the oil pressure, where at the very end of this flight, whatever kind of sensor is tracking latitude and longitude just output some kind of default value very briefly before it was turned off. So this is another anomaly we're going to need to clean up. Now, inside of this live task, there's a number of ways we can add optional visualization parameters to customize what's going on here. And behind the scenes, again, it's really just generating some code for us. And if you really want to grab the full power of MATLAB, you do need to start being willing to at least edit some of the code yourself. So like we did with the last task, let's say I'm done with the interactive part here. We're going to convert this to just standalone MATLAB code and make a few small edits ourselves. So if you ever see a command in MATLAB and you aren't sure how to use it, you want to learn more about it, like how might I customize the geoplot command, just right-click on it and go to Help. And this will take you straight to that command's documentation page. I hope you all make very heavy use of MATLAB's documentation. We're very proud of it. We think it's the best in the software industry. And every command has a documentation page that follows the same format. It starts with syntax, so different ways you can call it, detailed descriptions of what that entails, and then my favorite section, the examples. Every command has a lot of examples to go along with it. So we can scroll through and see different ways of visualizing geographic data. And we can search through until we find something that looks interesting. Like, okay, here we can see for geoplot, after we pass it latitude and longitude, we can customize things like the line width or the marker size, and we can change the background using something called GeoBaseMap. So let's say I want to make a few similar edits to the code that MATLAB gave me. I can pass additional arguments to geoplot here by just listing them after a comma. And if I start typing, MATLAB's going to try to help me and guess as to what I might want to do next. So let's say I want to increase the line width, make that line a little thicker and easier to read. I can rerun this section. Okay, that makes it a bit easier to see what's happening. And then I may want to add that GeoBaseMap command to change that background from just the grayscale. And here again, it's going to show me all the different options. I can scroll through them, try out something that looks interesting. Maybe let's try a topographic map. Okay, maybe that's fine. Let's explore and see what else is going on. Maybe I want to try something like satellite. So we can very easily and quickly explore what all these different options are without necessarily needing to look them up or remember them off the top of our head. And of course, we're really just kind of scratching the surface here of the types of customizations that we can do with MATLAB graphics. But let's say that's good enough for our purposes today, and we're ready to start cleaning up this data so we can get to the analysis. And let's say we want to start by cleaning up this latitude and longitude data. So there's no one right way to do this, but since this is happening at the very end of the flight, an easy way to just kind of ignore what happens at the very end and also the beginning is to just ignore any data when the aircraft is stationary. Because again, remember, our end goal is to build a virtual sensor for the true airspeed while the aircraft is flying. And if that's the case, we probably don't need help predicting the true airspeed when we're just sitting still on the ground. So if we go back up to where MATLAB printed out the contents of that table so that we can see it directly in our live script, we can get a histogram of what are all the different values in this column. So we can see for true airspeed, there's a fair number of values that are at or very close to 0 when it's just sitting stationary on the ground. The most common true airspeed is relatively high. We can guess this is during cruise, and you can see the distribution of other airspeeds it takes throughout the flight. And if I want to filter my table to remove certain rows, I can just change the bounds here inside of this histogram. Or just type in an exact value myself, let's say 30. I believe this is miles per hour. And we can use that to filter the rows to only when this condition is true. Below those numeric values, there's also an option for what to do with missing data. This is another common problem in engineering data. What happens if there's a blank, like a blank cell inside of that Excel document? Well, again, there's no one right answer, but if my end goal is to predict true airspeed, and the true airspeed is missing for that particular row, the rest of that data might not be too useful to me. So let's say for today, I just want to ignore any row that has a missing true airspeed. And as we've already seen a couple of times, as I'm doing this, MATLAB is automatically showing me what is the code I need to write to do that same thing programmatically. This is an example of what we call indexing or subsetting in MATLAB, where we want to take an existing variable and pull out just a smaller subset of it. You can see we do that by starting with the name of the variable, and then in parentheses specify the rows and columns we want to keep. We can use numbers, we can use names, but in this case we're going to use a condition. We're going to tell MATLAB, look at that flight data table, and any place where the true airspeed column is greater than or equal to 30, we want to keep all of those rows wherever that condition is true. Where it's false, get rid of them. As for the columns, we want to keep all the columns, and the way to do that in MATLAB is just a colon. And then we're going to take the result and we're just going to save it back to that same variable, so we're going to override what we already had. So this is a great way to learn how to do things in MATLAB, and it gives us a very easy way to just copy that command, and I'm going to paste it back up here. And so now I can rerun our script. This is going to run the whole thing. It's going to read that data back in from Excel. It's going to filter it now to only when true airspeed is greater than 30, revisualize it, and we can see that that was a very quick and easy way to clean up that anomaly in our latitude and longitude data. However, this type of thresholding is something we often have to do in real-world problems, but typically we don't know what kind of value to use ahead of time. I was able to make a pretty reasonable guess here, partly because I've solved this problem before. Normally, we would have to experiment with this a bit more. And in order to see both the code I'm going to play with and the output, I'm going to go back to putting the output side by side. And to make it easy to kind of interactively play around and iterate, I'm going to take this number and I'm going to turn it into what we call a live control. I'm going to turn this into a numeric slider. So this is a way we can add some customized interactivity directly into our live script. I'm going to customize this slider so it goes from, let's say, 0 to 400 in steps of 10. And every time I change the value, I'm going to ask it to just kind of rerun everything. So now I can drag this slider around. Let's say I want to go all the way up to the max of 400. And so now this is only going to keep the data when it's above 400 miles an hour. And you can see that cuts our flight down to only a very short portion of the flight. There's not a lot of data left. So maybe I want to back that down to something like 330 or somewhere around there. Okay, and we can see we still keep most of the flight, but we lose the parts right next to the airport. So maybe that initial guess of somewhere around 30 was probably pretty good. So there's a whole collection of these live controls that you can add to your scripts. And it's a fantastic way of adding customized interactivity in the form of buttons or checkboxes or dropdowns, edit fields, sliders, and spinners. So you can take your script and almost turn it into a very lightweight, very easy app, very easily and quickly. Let's say that resolved the anomaly in our latitude and longitude data, and we're ready to start working on some of that oil data. So let's say in our next section, we're going to clean up our oil sensors. Once again, we could write code to do that, but I'm going to do it the easy way. I'm going to grab our clean outlier data task. I'll pick out the variables I'm interested in from the workspace, and let's say I want to grab the oil pressure. And I also want to grab the oil temperature. We need to clean up both of those. And then this task is going to give me interactive ways to define the outliers. And this is very important that we can experiment and iterate with this, because there's no one right answer for how to define an outlier. You really need to play around with this option and see what's going to work best for your particular data set. And then also specify, once we find it, what are we going to do with it? Are we going to just delete it? Are we going to fill it in and interpolate it? And if we're going to interpolate it, how are we going to interpolate it? And then over on the right, it's generating a plot for us. This plot has a lot of information that's useful, but I find it's sometimes a little overwhelming, so I'm going to turn off some of it so that we're only looking at the original input data in sort of a light blue, and the cleaned up data, the final answer, in the darker blue. And we can see in this case, because we're just seeing the darker blue, that this algorithm isn't really finding any of those dropouts. So now's the point where we can very quickly iterate, try out different options. There's a lot of different detection methods for outliers. Instead of a moving median, maybe I want to try a moving mean. And looks like that didn't do much better. Maybe I want to play around with the moving window. Let's say I want to increase the size from 10 data points to 100. Okay, that worked a little better. You can now see, based on the color differences here, it's starting to catch some of those dropouts, but it's still not doing a great job. Now that I've made the moving window bigger, maybe we want to go back to moving median. Okay, and that seems to have grabbed all the main sensor dropouts. We're also losing some of these higher fidelity sort of wiggles in the signal up here. Is that important? It depends on the analysis that you're doing. Sometimes it might be, sometimes it might not. But in either case, really the important part is that we can very quickly iterate and figure out what type of algorithm is going to work best on our particular data set. Once we figure out where are the outliers, we then need to figure out, well, are we going to just delete them or fill them in? And if we do fill them in, how are we going to interpolate that value? We might just hold the previous value, kind of a zero order hold. This is kind of an old school engineering approach. Or interpolate it with something like a line or a linear interpolant or a spline or a p-chip. Let's just keep the default linear interpolation here. And so far we've just been looking at the oil pressure. Let's check the oil temperature as well. And it looks like this is working pretty well for that also. Okay, so we can stay here and we can iterate until we're happy with the results. Let's say that's good enough for today. I'm going to collapse that control and move the results back in line. Okay. And let's say at this point we're ready to start building that virtual sensor model. We're done kind of exploring and cleaning our data. We're ready to get into the modeling part. Now, so far I've been making heavy use of the tasks, and these are great when you have kind of smaller steps that you want to solve directly right there in the live editor. But sometimes the problem we want to solve is kind of a larger multi-step workflow that would really benefit from having its own more dedicated interface. And that's where MATLAB apps come in. So I'm going to come up here to the apps tab, and in the apps gallery, you can find over 100 different apps built for different applications. Things like machine learning and deep learning, math and statistics, control system design for things like tuning PID controllers, working with RF and robotics and automotive applications, dozens of apps for doing signal processing and frequency domain analysis, image processing, and working with visual data, connecting with hardware, computational biology, and many other applications. And these apps are great because they follow the same principles as the tasks. They give you an easy way to interactively solve the problem once, and then generate the MATLAB code you need to programmatically go do the same thing. Today, we're going to use the Regression Learner app. This app is designed to build machine learning models when the output you want to predict is a numeric value, like the true airspeed. We're going to start by importing data from our workspace into the app. And we want to use that cleaned up data that the clean outlier task created for us. I forgot to mention earlier, we can name that whatever we want. By default, it gets named new table, so we're just going to select new table here. We could have changed that if we liked. And then we're going to pick out what in this table is the outcome we want to predict. And we want to predict true airspeed. Then we want to tell the app what inputs is it allowed to consider, because some of them we might want to disallow. For example, I want my sensor to work exactly the same way no matter where it is in the world. So I'm going to disable latitude and longitude and tell the model you're not even allowed to consider those measures. Over on the right, we have options for how to validate and test the model. This is an important topic in machine learning, but for the sake of time today, we're not going to get into that. And then all of MATLAB's apps have a kind of uniform workflow up in the tool strip going from left to right. So you can see we can start with things like feature selection or principal component analysis, trying to figure out what parts of our input data are important for predicting the output. We can then select a model or multiple models from a large gallery. We can then train those models, plot and visualize the results and analyze them, and then export whatever those results are outside of this app. For today, we're not going to go through kind of all the different types of models you might want to train. I'm just going to pick all the ones that are fairly quick to train, and then train them all. And behind the scenes, MATLAB is going to automatically open up some extra MATLAB workers with this use parallel option. So we have extra MATLAB computational threads on my multi-core machine, so it can start training these different models simultaneously in parallel. And whenever it's done, it's going to pass those results back to us. So here you can see this sort of baseline linear regression model as a single numerical summary, this root mean squared error. It's off by about 13 to 14 miles per hour on average. And on the right, you can see in blue the correct answer it was trying to predict, and then in yellow, its actual prediction. So it did okay in capturing the general shape, but not great. If we look at the next model, the fine decision tree, and we look at its response plot, you can see it did a much better job of predicting the correct answer. So there's a lot more we can do here in the app to explore different models, test them on data it hasn't seen before, even get into explainable AI and try to explain, well, why is it making certain predictions and not others? But in the end, we'll eventually have a model we're happy with, and we can either export that model back to our MATLAB workspace or generate a new function. So this will give us all the MATLAB code we need to programmatically train the same type of model with all the same options, but on any new data set we want. This generates a new function file. This is how you can create custom commands in MATLAB. So you've seen already some built-in commands, but you can write your own custom ones as well. Functions in MATLAB always follow the same format. It starts with the keyword function, and then any outputs listed in square brackets. Here we're going to get two outputs back. We're going to get the trained model itself, and then that statistical measure of how well the model did. This is followed by the name of the function, and then in parentheses, any input arguments like a table of training data. Following that, this green text, which is preceded by a percent marker. These are just comments explaining what's going on. It's not executable code. And you can see automatically generated for us are comments explaining what are the inputs, what are the outputs, some examples. So it's going to show us how do you call this function to train a new model, and then how do you use this model to predict on new data. And if you want, you can scroll down and start looking through the code, but we're not going to worry about that today. Before we use this function, we need to save it. Again, this is by default just going to go right into our current directory. And then I'm just going to copy these two commands from the comments that were automatically generated for us over into our live script. So the first one is going to train a new model, the same kind of model, on new data, and the second one will make predictions for us. We're then going to give it the correct name for the data we want to pass. We want to train the regression model on the cleaned data on the output of this task. And then normally in machine learning applications, you would predict on new data the model didn't see while it was being trained. For simplicity's sake today, we're just going to use that same table of data again. And you can see now we have all the code we need to programmatically train that same type of model and then make predictions on any new data. And the final values you see here, these are the predicted true airspeed values. Okay, so that kind of solves the core problem we were trying to get at today. We were able to import some data from Excel. We were able to visualize it. We cleaned up some sensor anomalies, and we trained a machine learning regression model to predict the true airspeed. At this point, we might want to share the work that we've done with other people. Before we do that, we probably want to clean it up, add a lot of comments to make it very easy to understand what's going on here. For the sake of time, I'm not going to do a lot of typing myself. I'm just going to open up a live script I already have where we've done a bit more of that already. So you can see we've added more comments explaining what's going on, but we're solving the same problem. We're importing that data from Excel, and we're visualizing it and looking at the flight path, and then cleaning up those sensor anomalies. So we're doing all the same things. And if I want to take this and share it with other people as a report, I can easily export this to PDF, Word, HTML, LaTeX, Markdown, or Jupyter Notebooks, whatever format is most useful to you. And if I export this to PDF, this is exactly how we generated that report that you saw way back in the beginning. So once you've done your analysis in a live script and you've documented what you're doing, generating a report is just one button click away. And with that, that's going to end the MATLAB demo portion of today's presentation. Let's go back to the slides to wrap things up. So in today's demonstration, we looked at how MATLAB simplifies engineering data analysis with low-code tools. We looked at importing data from an Excel file. We did some basic visualization and analysis and trained a machine learning model. And we looked at one simple way of generating a report. If you're curious, along the way, the products we used, almost everything was done with the base MATLAB product. The one exception is the Regression Learner app, came from the Statistics and Machine Learning Toolbox. That is an add-on product to base MATLAB that contains hundreds of commands as well as a number of different interactive tools and apps for doing statistics and machine learning. But throughout that data analysis workflow, there are many other low-code tools that we didn't have time to see today. When it comes to access, there's also the import tool. This is a large standalone app for importing data from places like text, CSV, and Excel. There's also a database explorer. This is equivalent, but for importing data from ODBC and JDBC SQL databases. It's a fantastic tool when you have more complex table joins and selection statements and you're looking for a bit of help. And if you are ever working with hardware or hardware data in MATLAB, there's a whole family of apps for helping you import that. And you can work with any type of data in MATLAB, not just flat tables from places like Excel. In addition to observational and time series data, you can work with image and video and n-dimensional data, and you can work with data coming from anywhere. Databases, Hadoop, cloud, and streaming off the web. Any kind of data you got, MATLAB can work with it. When it comes to the explore and discover phase, there are a lot of tools for data analysis. My personal favorite we didn't have time for today is the optimized live task. This is a great tool for helping you find optimal values or parameters. It helps you figure out what is the best objective function and constraints to find that optimal value. In the world of engineering, we have dozens and dozens of low-code tools for designing control systems and doing signal processing and image processing, computer vision. My personal favorite that you see here is the Signal Analyzer app. This is a fantastic tool for exploring time series sensor data in both the time and frequency domains. And in AI, we have a lot of interactive tools for things like ground truth labeling and designing, training, and validating neural networks like the Deep Network Designer that you see here. When it comes to sharing your work, we spent a lot of time in live scripts today, which is just one way of sharing it. You saw how you can create different sections and interleave code and outputs. But you can also do a lot of rich formatting, text formatting that we didn't have time for today. with things like outside images, equations, hyperlinks, tables of contents, and so on. You can even create animations that embed and will export, customize fonts, and as you saw, export to a number of different formats. Now, as your needs grow, the MATLAB language grows with you. You can start very simply with just a couple of easy commands. This is actually how MATLAB got famous in the first place, is it made linear algebra very accessible. And then you can move up to creating simple scripts. And as we saw today, anytime you start typing in MATLAB, MATLAB has a lot of built-in tools to help you figure out what is the code that you need to write next. You can create your own reusable functions and custom commands in MATLAB. You saw today how an app can do that for you, but you can also write your own from scratch. And then you can grow all the way to writing very robust professional software with object-oriented programming if you need to go that far. You can also grow from coding by yourself to coding in a team and collaborating with others. MATLAB projects help you keep track of all the different files and sort of the reproducible environment you need to work on the same project. Source control is great for tracking changes to a project over time. MATLAB has a very robust software testing suite to make sure your algorithms are actually producing correct answers. And you can integrate MATLAB with other code and environments. And this is where Excel comes back into the equation. If you saw what you liked today in MATLAB and you want to start working in MATLAB, but also continuing to work in Excel, there's a couple different ways you can co-develop in both. One is to control MATLAB from the Excel environment through something called Spreadsheet Link. Spreadsheet Link will actually give you a little MATLAB menu inside of your Excel tool strip. And this is great if you want to build new algorithms in MATLAB, but you want to continue to have Excel be your driver application. From Excel, you can connect to a MATLAB session, you can send data back and forth between your Excel workbook and the MATLAB workspace, and you can tell MATLAB to run commands and return the result back to you. You can also go the other way, and you can control Excel from MATLAB. This is great if you want to start building new applications in MATLAB, but you want to reuse existing work you've already done in Excel without manually recoding it. You can do this through what's called the COM interface in MATLAB, which is an interface that lets you connect MATLAB to other applications that follow the COM standard. And let's say you wanted to leverage a macro you already have in Excel. It just takes 3 simple commands in MATLAB to first connect MATLAB to the Excel application, and then tell Excel to open your workbook, and then tell Excel to run your macro and return that result back to MATLAB. So if you want to co-develop in both platforms and get the best of both worlds, there are multiple different ways you can do that. You can also take the work you've done in MATLAB and deploy it to people who don't have access to MATLAB. Let's say you are the MATLAB user on the left here, and you have a colleague on the right who's an Excel user, and they don't really have a reason to have or buy their own copy of MATLAB. Well, you can take the work that you've done in MATLAB, whether that's algorithms or visualizations or whatever else you want to create, and you can run it through something called MATLAB Compiler. MATLAB Compiler is an add-on to base MATLAB that takes any of the work that you're doing, it supports 99.9% of what you might do in MATLAB, and turns it into different types of software libraries. Standalone executables, Excel add-ins, and with the MATLAB Compiler SDK, you can also create libraries for .NET, C and C++, Java, and Python. We're talking about Excel today, so what the MATLAB Compiler would do in this case is it would generate a very light VBA interface wrapper around your MATLAB code and then compile that into an Excel add-in. That Excel add-in is then something you can use just like any other Excel add-in, but all the add-in is really doing is serving as an interface between Excel and your MATLAB code. You can then take that Excel add-in that the compiler generated, and you can give that to whoever you want, however many times you want. They can use it inside of Excel like any other add-in, and they don't need to buy their own copy of MATLAB. But because behind the scenes, it's really just running your MATLAB code, they do need access to something called MATLAB Runtime. MATLAB Runtime is a freely distributable version of the MATLAB engine. Anyone in the world can go download that off our website and install it wherever they want. There's no restrictions. But all the runtime can do is run things that have already been built with the MATLAB compiler. You can't write new applications or edit existing ones with MATLAB Runtime. It can just run the existing libraries. So using this workflow, you can build things in MATLAB and then share them with other colleagues who are in other platforms like Excel for them to use for free. So we covered a lot of ground today. Let's remind ourselves of a few key takeaways. We started by talking about how MATLAB is a platform for engineering data analysis and some of the special challenges that come with engineering data. We spent most of our time in MATLAB looking at how we can leverage low-code tools that are built for those engineering challenges. And we ended by talking about how you can combine MATLAB and Excel and co-develop in both to get the best of both worlds, or take tools you've built in MATLAB and deploy them to Excel users who don't have MATLAB. Let's wrap up with some learning resources you can use after today. The next best place to go after today is probably our free on-ramp courses. So if you want to get started with MATLAB and learn the basics, these are free training courses you can find on our website. They run entirely in your browser, they're interactive, and they all last 1 to 2 hours and walk you through the basics. You can start with the MATLAB on-ramp to learn the core environment, and then jump into more advanced applications like signal processing and machine learning. If you like what you see there, there are also much longer and more thorough paid options, such as MATLAB Fundamentals, which has 3 days worth of material and will take you from knowing nothing about MATLAB to being a competent intermediate user who knows how to import, analyze, and export data, write complex programs, perform calculations, and create visualizations. Along the way, I hope you leverage the MATLAB Central community. MATLAB Central is our community site where over 2 million monthly MATLAB and Simulink users come together. A few of the highlights is MATLAB Answers, which is an online Q&A forum where most questions get answered in under an hour. So if you ever have a question about MATLAB and you can't find an answer, MATLAB Answers is a great place to go and pose that question. It's also the file exchange where you can access code and tools other MATLAB users have built and provided to the community for free, and a number of other interesting areas of the community site. And of course, MathWorks is here to support you in many different avenues. We have full hands-on and on-site training and workshops, free guided evaluations, full paid consulting, as well as on-call technical support. And that's about everything I had for you today. Thank you all for tuning in.